All right. Hello. Good noon to you. This class is the worst because I can't say good morning or afternoon. I always have to say something awkward, good noon. Good noon to you. Well, welcome. As you may know, my name's Sam Snow. I'm a professor here in environmental engineering, and most of you all, I'll get to know you a little bit. I've got a little activity for that. But a lot of you are civil engineers that have to take the class and probably don't care a whole lot for chemistry. So I've actually been teaching this course specifically since I arrived here in 2016. So I think I have a pretty good understanding of about where you're probably coming from. Some of you are probably going to be pretty interested. Oh, that's cool stuff. Some of you are probably like, no, anything but chemistry, please. I wish I could run out the door and leave. I get that. So we'll talk a little bit about all that. But welcome. I'm glad to have you here. This is about 50, maybe a little more students. That's probably a little over my ability to learn everybody's name, but I'm going to give it a shot to get to know you. So please be patient with me, and please interact as you desire, and as you do so, that'll help me get to know you better. Okay, so EVEG 3110. This is water and wastewater treatment. Is kind of the topic, right? My plan for today is to go through the syllabus, kind of get on the same page with that, go through a bit of an activity to get to know you, show you what some of our participation events might look like, maybe have a couple laughs here and there with all that. Give you the big picture of what environmental engineering is about, focus that a little more narrowly to water and wastewater treatment, and then dive into some of the basics. Since we did not have class on Tuesday, I think we can catch up pretty well just kind of diving straight into it today. So that's my plan. Okay, so what I'll do is give you this the big picture overview here. Actually, I think I'd rather go through the syllabus first. So we'll do the syllabus first. Show you kind of my approach here. So this is posted to Moodle. So you have this. I updated it just today. A few basic information points here. So my office is in PFT. Most all the civil and environmental engineering faculty are kind of along one hallway or that area. So I'm just down that hallway. If you happen to have known where my office was before, which probably none of you, it moved after last semester. So just in case that mattered. Office hours typically will have the block between 11 and this class open, and I'll be there Tuesdays and Thursdays with the expectation if anybody needs to drop by, that's a pretty good time. Happy to make an appointment outside of that, whether virtual or in the office. Either are great. And you are welcome to stop by, just that you know that if I'm too preoccupied with something, you might either have to wait or reschedule. So pretty typical there, but definitely make use of it. There's a couple concepts in the class that if you get stuck on them this first few weeks, it could throw you off for a lot of the class and be a frustration for most of the entire semester. So definitely give yourself a shot. If you're feeling like you almost have it and don't quite have it, no harm in coming to office hours. Class time, obviously, here and now. But one thing I'll say is, since the pandemic, basically, and all that, I started live streaming my lectures as a way to get them to students. I preferred that way more than Zoom because then I can not be interrupted by random people entering and all that. So we're actually live right now. And I just switched over to streaming on YouTube. So I have a YouTube channel that will be a repository for the lectures in case you need to go back and review them. And it will be an opportunity if you are sick and have to miss class in person, you can catch it there. That said, you'll see I do expect participation. So I have some in-class participation events I would like to have you here. I think you'll learn more that way. It's not, as you'll notice, there are ways to get a decent grade with not showing up. I don't think you're doing yourself a service there, so I discourage that, but that's kind of the way it is. So there's a lot of flexibility there for you. I hope that you use that for benefit and not for your own detriment. Okay, the textbook, likewise, is I have a required text. I do highly recommend it, especially if you are ever at all going to interface with environmental systems. This is not just a water and wastewater treatment book. This is Intro to Environmental Science and Engineering, and it does a good job covering the basics. So if you ever have to design a system that has to tackle something with air quality, or maybe butts up next to it and you just want to refresh your memory on, well, what are the, how do I approach problems in air quality? It has some content there for you. You'll find a lot of useful problems. I base almost all of our course material from it. So if you were to follow along the chapters, you'll see I've got chapter labelings for most of our lectures planned. You'll probably find it very helpful to read it and look at it. Might be something you want to get with a group of friends and just share one. Might be something you want to get for yourself. I do recommend it. These online materials here, totally optional. Most of them are free on the library. I wish I could teach from one that was free, but these are all a little bit more esoteric and dive into way too far for the context of this class into the topic. So, but if you did want to dive further in, let's say to membrane technology or something, some of these books are good resources for that. Okay, objectives are pretty straightforward. You all have to take the PE or the FE eventually, right? So you want to do well on this section. That's basically objective, right? It's to train you for that. But a little more, I mean, that's certainly true, but a little more seriously, the way I look at it is this is a required portion of your coursework, and some of you are just here because you're interested, maybe from a different program. And I want to give you what it looks like to deal with environmental technologies, right? What does it take to get clean drinking water, and how do we treat our wastewater? And I find it pretty interesting. I'm passionate about a lot of the topics here, so I hope that will be make it a little more enjoyable for you along the way, because I have a few stories. I was in Flint, Michigan when that stuff was happening, so we'll have a nice seminar on that. And in terms of the formalities of the course, what we're trying to do is give you the skill set to work on a design problem in the context of a water or wastewater treatment facility. We have such and such a requirement, have to treat to a certain extent. Well, how does that look? What parameters do we need to adjust? How do we calculate? And you'll be happy to know that even though the material is probably unfamiliar to the civil engineers in terms of how we approach it, it still kind of boils down to math, right? And some physics. So you won't be, it'll feel a little unfamiliar, but it's certainly within your capability. Okay, so grading, we have 3 equally weighted exams. The final exam will be a little bit cumulative, probably about halfway so. The entire class is a bit cumulative in the sense that what we learn in the first few weeks is used over and over again, and some sections of the class, for example, I'll talk about sedimentation in a couple weeks, and sedimentation is used in both drinking water and wastewater treatment. So you'll notice it feels like 2/3 of the class is drinking water treatment. That's sort of my specialty, a little more so than wastewater. And then 1/3 wastewater, which is kind of ironic because everybody sees just the wastewater tag on the flow chart and thinks this is a wastewater class. It's really both, and it'll feel like we're focused more on the drinking water side, but really a lot of these processes apply to both. So it's that's just kind of the way I've structured it. Homework and class participation scores will be then combined as a last quarter of the grade. Now, in the homework, I used to give it a little bit more credit, and it was a struggle to be fair to any student who was really engaging themselves and trying to do it with their own effort and not cheating in any sort of a way. And the trouble is the solutions get out there, and it's way too much time on my end to either check to see if you were copying exactly verbatim somebody else's solution, or to come up with a brand new homework sheet and solutions every semester I teach the class. Neither of those were working for me. So what I did, I don't like that I've taken grade, I've adjusted the grade away from homework scores for you, because it used to be the homeworks would be 100 points. Because I like to give you the opportunity to work hard and for it to show, but I was always shortchanging the students who were actually working hard. So I'm going to give homeworks that are probably solutions out there, and I'm going to grade them for completion and not for correctness. So that means it's up to you to use them as a tool to learn, which is the purpose anyway. That's what I want to be grading you on, is how much you learn. That's my aim. So it's unfortunate in my eyes that that's the way it is, but that's the situation. And so my challenge to you is to make good use of the homeworks rather than just making minimal effort, because the exams do tend to be difficult. I like to challenge with the exams, and then if I made it too challenging, I will adjust. But generally, that lets me see how much you learned. Right? There shouldn't be many people getting 100 on an exam. If I did, I made a mistake in the easy direction, and I'm not going to correct that exam for that. But my intent is to gauge how much you learn. Right? So, okay, and then class participation, I think I mentioned a little bit. We're going to do an activity here in a moment, but we might do in-class quizzes. It might be a Moodle, sort of a take-home type of a quiz to participate in. Maybe I have one or two reading assignments for you throughout the semester as a little addition to, or a tangent to, the topics that we're covering. So that will be a combination of those activities. All right, so we'll come back. We'll do kind of a sample activity in a moment. I use Moodle, so you'll see the page is pretty full of materials. I'll go ahead and actually flip over to that. So you'll be able to see kind of my current situation here. Of course, it'll look slightly different for you. I've got the syllabus here. I've got a formulas and tables sheet here. This will be what you get on your first exam, and I'll update this for your second exam and so on. Every exam you'll have a periodic table. You'll have a density and viscosity chart for water, and you'll have some sort of formulas. And this way you don't have to think about bringing a formula sheet. You'll have this as a study guide to say, okay, what's on it and what's not on it? What do I have to commit to memory? And especially, there's all these symbols. A good way to study would be to make sure you're very comfortable with what these symbols are and how they're referred to in different homework problems and things like that. Okay, so this hopefully will be a good study guide and a tool for you. I also have an Excel sheet listing several problems from the book that might be relevant to particular topics. So take a look there if you're needing recommendations on what kind of problems to look at. And then I will keep a YouTube playlist here for basically the lectures in our course. If I give, let's say, an exam review and I don't want it to be public, just that you have the link to that particular one, I will link that directly. Let's say if we have, for example, it's not shown to you right now, but I have last semester's exam 1 recap. So I might post that as a separate link, and if you have the link, you can access it that way. Okay, but otherwise everything will be on this playlist, and you'll be able to see that here. Now, another thing I'll note is we can actually see, if we want some classroom inception, that we're currently live. It's going to be a few seconds delayed, but we could go over there and view that video. All right, and if you do participate ever online, you should be able to make comments in the comments there live, and I will get them. You'll see what I see here. I'll get those comments over here, and I'll be able to talk back to you because you're asking me a question, and I can respond there. So sorry if this is making you dizzy. On my end, I'm just seeing what's projected up there, so I can kind of makes it nice because now with the PowerPoints, I will write on the PowerPoints with a little tablet, and I can kind of see what I'm doing without doing that. Okay, so that's just kind of the basics of how I'm going to be conducting the class. Hopefully that's convenient. You'll also find that I have a section, let's say section 1, here we are today. My plan is to upload a blank PowerPoint slide, or not blank, but a slide deck for the notes for today that has not been written on yet, and then so you can follow along with that if you'd like, making your own notes. And then after the class, I've written all my notes, I'll upload that, and so you'll have my notes posted there. Okay. So again, hopefully this is convenient. I think there's probably some, with all these conveniences I'm building in, there may be some temptation to just procrastinate on the studying or whatever. So I'm just going to trust that you're all adults and can do what you need to do to learn well and all that. All right. So class was canceled Tuesday. So today we're going to try to cover a bit more than just introducing the course and get into the units and mass balance. We can take a look, but basically I'm going to give you some background, a bit of chemistry refresher, a bit of a background on our basic approaches, what we call mass balances. We use quite a lot in environmental systems, and so on. Our first exam is currently scheduled for September 26th. We'll have to see. I might need to change that given the first day was canceled. We'll try not to. And the second then would be on November 2nd. The final exam schedule is even, at least when I set this up last week, was scheduled for December 6th. So I'll double check that when it comes closer to time, but that's what LSU's page had. Okay, any questions on this? The syllabus, yeah.
When you have like an exam problem that are multiple parts, are you going to score the parts dependently?
That's a good question. So I typically score exams. I do give partial credit, and what I do is I score different parts based on my perception of how much effort that required. And if, let's say, you needed to get part A right to get part B right, well, first of all, I try not to set those up that way. But when I do, then what I will do is check to see, well, either if you had the right number here, would your new answer be correct? Or at minimum, was this second portion of this, was that a correct procedure? And mark accordingly. Yeah, it's a good question. Anything else? All right. Well, let's take a quick couple minutes to get to know you. So grab a device of some sort and go to kahoot.it. And then you can punch in the game pin right there. Now, in the future, I may ask you to put in your 89 number for your name. That way I can export it to Excel and grab attendance and scoring that way. For now, it doesn't really matter too much, so long as you're not inappropriate, I guess. I won't be taking formal attendance for the first week or two while the drop ads are happening. Whenever I try to do that, it gets my roster pretty confused. Then I go and delete somebody, then I inevitably get somebody's grade wrong. So I'm gonna hold off on that. That also means if you are, let's say, a chemical engineer and none of this stuff that I'm covering the first week or two is new and it's really, really boring, you're welcome to come back when things are actually interesting. I get that. Because if I'm talking to chemical engineers, I'm like, hey, this is a mass balance. You're probably like, all right, why am I here? Okay, so use at your discretion. Anybody else need a chance to get in?
It says that the player limit has been reached.
Man, the free stuff, they just don't work very well anymore, I guess. All right, so, wow, that's a new one. All right, so last time I did this, there was no play limit. Sorry, you're going to be excluded, and I guess we're excluding Kahoot for real participation from here on out, because they just really, really want the money. All right, but you're welcome to shout out your answer if you want to. Okay, so what's your major? Ideally, there's no EVEG majors because we have a section dedicated to that in the mornings. Okay, so primarily civil engineers, 5 chemical engineers who are ready to jump out of class already because of what I just said. Okay, others. Who's others? What are you?
Biological.
Okay.
I'm second, sorry.
Great. Yeah, this is actually pretty typical. I often have 1 or 2 biological engineers that are interested, a few chemical engineers, and my other section that is dedicated more to EVEG. With permission, I can swap, or I can allow somebody in. We're just not supposed to have EVEG students in here, and the civil engineers wouldn't want to be in the other one because it's a lot more chemistry. So if that's interesting to you, you're welcome to let me know. Okay, how many years have you been at LSU? All right. Yeah. And this is interesting. For the civil engineers, a lot of you take it your senior year. The EVEG, you take it junior year, so it's just kind of interesting to see that. All right. I've been here since 2016, so I guess 7 years now. And I just turned 36 this summer. To give you a little bit of info here. Okay. And where are you from? And when I say that, just where did you grow up most of your early childhood, or whatever you want to answer? I grew up outside of Atlanta in Georgia. And just as a side note, yeah, so that makes sense. So I guess my answer is 3 states away technically, so not quite fitting into the nearby category, but it feels pretty nearby. And I meant to say earlier, my major in college, so as an undergraduate, I did a program called Earth and Atmospheric Science. So technically, I'm not truly an engineer, and I think I might be able to sit for the FE if I pay people to review my transcript and tell me that, oh, you probably need 1 more course in engineering, then you're allowed. I did my graduate program in environmental engineering, so but that was not an accredited program. So when I began my undergraduate, there was no accredited environmental engineering program. Otherwise, I may have considered that. So just an interesting little fact about that. Okay, so what topic are you least comfortable with? Is it chemistry, physics, engineering, math, or are you pretty much a boss? See, how many of you think you're getting A's, right? All right, got 6 confident ones, and 33 civil engineers, excuse me, and no. Okay, that's pretty typical. That's certainly understandable. And we don't really do too much direct physics. Whatever we do cover is kind of like, here's a physics topic that has to do with sedimentation, for example, and then we just look at a bit of math and get to the equations we need to. Okay, so speaking of chemistry, here's some sort of a chemical structure, and I want to know what you think when you see this. Okay, so some of you heard each other maybe laughing about the joke, or just a lot more of you are more chemistry savvy than you thought, right? Okay, so 16 of you felt like, hey, I know something about chemistry, right? That's iron and oxygen, right? That's some sort of iron oxide. Fair enough, fair enough. 5 of you were real chemistry whizzes and recognized, yeah, that's not a real thing. That's not even possible, right? 15 of you got the joke. 14 of you just hate the chemistry and didn't want to bother. But those of you who got the joke, it's a Ferris wheel. Seen one of these in a state fair, right? So this is actually how I remember ferric versus Ferris, right? So it's my older sister one time got me a T-shirt, which basically had that on it, not similar. And it's little Fe2 pluses around in a circle, and it's we call Fe2 plus ferrous iron, and Fe3 plus is ferric, and so it's a Ferris wheel. Okay. Could make seeds. All right, so most important part, do you enjoy a good pun? It's the real test of how well you'll do in the class. All right. So 4 of you were trying to get away with, this is stupid, let me out, but I made you say a pun anyway. Yep. All right. Yeah, so some good ones there. Okay, so I would say that we'll use this in the future for attendance, but apparently we have a numbers limit, so we'll probably not do Kahoot again. Sorry about that. I'll figure that out. Definitely not giving them any money, but maybe we'll maybe the class size will drop to just under 50 or something, and scare you enough on the first exam. All right. So thanks for your participation there. Actually, I probably might use it occasionally if I just want to get a little quick feedback from you, like, hey, how did that test go, or something like that. So we might use it, but like I said, probably not for attendance. Okay, so with that, I want to get into our topic, unless you have any questions about the big picture of the class, logistics. All right, so water and wastewater treatment. Really, I think all of environmental engineering revolves around taking some amount of stuff in some media, so some stuff in some other stuff, like some bacteria in water, like some chemicals in the ground, like some dust in the air, stuff in stuff, right? We have some system where we have maybe a little jar of water that's got some stuff in it. We send it through a process, and the goal of that process is to either separate, transport, or transform the stuff. So maybe we're left with a little pile of our stuff that we can go send to the landfill in a nice, safe, protected way. And if you even think about a landfill, all that's doing is protecting the environment, the soil, anything else around outside of that landfill, and putting a nice boundary and keeping the stuff that we wanted in the landfill out of anywhere else, right? It's kind of the same thing, right? So as we approach the class, any of our technologies or any of our problems are going to relate to this concept in some way or another. Pretty stupidly simple if you think about it. So we'll see this in a variety of ways. And honestly, it all comes down to conservation of mass. Sometimes we'll do conservation of number in certain cases where that makes more sense. For example, if we're counting how many viruses are in a bottle of water and we're trying to destroy some of them, we're not going to weigh the viruses, and there would be kind of no way to do so anyway. Rather, we will count them, and so we'll have a number of them. And our assumptions, our what we work on will really revolve around how many of those are still there and viable, infective, or whatever. So we might do conservation of number, but kind of same principle. We're not creating or destroying mass, and unless we have bacteria reproducing as a reaction rate, we're not magically making bacteria appear, right? Okay, so that's a good thing for you, because that means even the chemistry stuff is really all just kind of surrounding, geared towards having a system, knowing how much of stuff we put in it to accomplish a task, and how much we're getting out, right? So even the chemistry is not going to feel like you're in chemistry class. It's like, oh yeah, I have to use that, and we'll have a refresher to remind you in case you haven't had it in years. All right, so big picture, water treatment for drinking, we have two specific tasks typically. One is to protect health. These would be health standards. We'll talk more about them in a few lectures. And they are kind of mandated standards we have to meet in order to protect human health. There are also aesthetic standards, because it might be perfectly safe to drink brown water, but who's going to want to, right? Likewise, it might be perfectly safe health-wise to have a bit of rust or orange color in your water, but that's not going to be so nice when you wash your clothes with that, right? So there's some real pretty important reasons we would want to protect that. And if you're thinking to yourself, really, brown water? Why would that be relevant? Well, you probably have all consumed some brown or other colored water very recently, right? So if you've had coffee or tea or lots of different types of soda, that's water that's been made a different color, right? So you could put food coloring in the water, and it's health-wise, it's safe, but it's not going to meet the aesthetic standards. So we have a couple standards there. Wastewater is in some way similar. We want to protect intended uses. We want to be able to safely recreate in natural waters. We want to be able to navigate through them if that's one of the intended uses, to fish in them, to swim in them, to use our natural bodies of water for a variety of reasons. And if we're discharging wastewater to them, that can impair the intended uses. And so our regulatory goals are to protect them. Sounds pretty obvious, but rivers should not be flammable. And rivers were flammable about 50 years ago sometimes. And there were many cases of oil and grease layers on top of water, on top of rivers and lakes that caught fire. And how in the world are you going to fight a grease fire sitting on top of a lake? That's not fun. Okay. So pretty obvious, but there you go. All right, we covered all of this basically in the looking through the syllabus, but here's a little picture of the front cover of the book. So talked about all that. And so what I'm going to do is switch to our next set of slides and carry on. All right. So, again, I apologize. Some of this today, especially for the chemical engineers, I imagine, is going to just be feeling very rudimentary. But I'm starting here on purpose because I understand that some of you like to build bridges and haven't thought about what you're drinking and, ever really, or what might be in it, or how to quantify what might be in it. So I'm going to build you the tools from the ground up, essentially, so that we can approach our word problems with a bit more ease. So I mentioned this is all about conservation of mass. So that's essential. And so as we move forward, we're going to talk about what we call a mass balance. And what we're referring to there is some accumulation of mass into a system over time. Sometimes we will have a net zero accumulation, but we can still set up the mass balance to understand the conservation of mass. We'll have a problem in a little bit on that. If you think about a stream that runs into a pond, and there's a stream that's exiting, we could call the flow rate of that stream Q for a flow rate. The very simple way to look at this, let's say we have a pond that's just been there, it's had the same water level for a long time. It has a little dam that holds the water, it holds a certain amount of water, and water flows in and water flows out all day long every day, right? That's typical of a lake or a pond. Now, if you were to suddenly remove the dam, you have a sudden accumulation in the negative direction of water in that pond, right? It's all leaving. It's leaving at a faster rate than it was coming in. And so you, for a little while, you have a non-steady state of how much water is in that pond. That's intuitively obvious, right? The water's leaving. And we're going to map out how to deal with that stuff with math, okay? Likewise, if there was a stream running through maybe a little valley and you put a dam there, eventually you're going to let out the same amount of water to let it exit as is coming in upstream. But in the meantime, you're accumulating more and more water. That's what we would term, we would describe that with an accumulation term. We're going to do that kind of stuff with slightly more advanced processes. Maybe we have some concentration of a contaminant in there, and instead of putting a dam, we have a reaction that destroys that contaminant, okay? So maybe we're disinfecting with chlorine. And so instead of talking about the balance of the water, which thankfully most of our problems, we're just going to keep the water the same. But the amount of bacteria then would be the thing changing. And so as we think about a mass balance, be thinking about how much stuff is entering our defined area and how are we mapping that out mathematically. Okay, so in that, we're almost always going to be looking for the units. So units are absolutely essential. So as an example, if we have some flow in this volume, there is an equation that you'll need to learn. It's for hydraulic retention time. We're going to cover it again later, but I'm just kind of giving you, I guess, a little example here. So that's going to be in units of time. Let's say that's seconds. How long does the water stay in the pond on average in seconds, right? And if you think about it, that's probably going to relate to the amount of volume we have here, and I'll say that's cubic meters, and the flow rate. You know, just intuitively, if you have a hose trying to fill this guy, and you've got some water going in and water splashing back out, on average, the water's not staying there very long if I've got the hose turned all the way on, right? That's a short residence time. So you know that if I were instead to put that hose in this room and try to fill the room, it's going to be a longer residence time because the volume is bigger, right? It's going to, on average, the water will stay here a longer time. So you kind of know already, without even thinking about anything engineering or environmental, that concept. So we don't know the equation, so let's take a look at the units. We need and we call this hydraulic retention time theta, by the way. So theta will be some function of flow rate and volume. We just don't know yet. So we know that it's going to be in seconds. And let's say our flow rate is in cubic meters per second. That's the amount of a volume of water per time. So we can just look at the units to arrange this in a way where we have time on top, right? So this should be, to get time on top, we have to divide by this 1 over time. So whatever else is happening, we have to have it divided by the flow rate. So that's the only way we get a seconds on top here. So we divide by that flow rate, and now if we did divide by a flow rate, that's giving us, so 1 over Q would be seconds per cubic meter. So now we need to get rid of the cubic meters, and then we're good. So we just multiply by the volume. Turns out that's our equation, and this is why I'm not giving it to you for the exams, because you should know this. Or you should be able to find it, right? The hydraulic retention time is volume divided by flow rate. And the reason I'm going so far into this, such an obvious thing, is to show you, I want you to be checking your units and be thinking about units in terms of how are you approaching a problem. I forgot something. I forgot what this term meant, but I remember everything else. I must be able to find what it is based on the units, right? So if we were to go back to that formula sheet, if you knew 4 out of the 5 parameters there, you could solve for the units of the last one, and then at least you have some place to start. So use your units. I recommend when you start solving a problem, at least the first time you're writing up your values, write in your units. Maybe don't do it every single line. Maybe it's the first time, and the last section, write your units out to make sure you're on track with what you're supposed to be solving for. Right? Will improve your grades. I can guarantee that. Okay. In terms of the mass balances, we're almost always looking at some form of mass per time. Maybe in some cases it'll be a concentration per time or a number per time. But basically when we're talking about a rate, it's almost always mass or number per time. That means in our example up here, at what rate in terms of, let's say, kilograms of water per time is it filling? At what rate is the chlorine decaying, right? That's milligrams of chlorine per time. So it's going to be mass per time for our rate equations there. Okay, a note on chemistry. Almost all we do with chemistry is going to be a matter of units. And if you are hating chemistry, then you'll hopefully be pleased to know that the only thing that you might find actually a little bit new or complicated will be chemical equilibria. And really that also just kind of boils down to properly using units. And you have a standard equation that you can then relate given some values. Okay, so more basics. I expect you to know pretty well your metric units. Hopefully this is pretty obvious. At minimum, kilo, centi, milli, micro, and probably nano. You should kind of have, as working knowledge. A centimeter is a 1/100th of a meter. A millimeter is 1,000th of a meter. A micrometer is 1/1,000,000th of a meter. Nanometers, 1/1,000,000,000th. So make sure you know those. Another comment on units here. This is the table you'll be given on your exam sheets. I think we looked at that for a moment. This is a density and viscosity table for water. That's primarily what we'll be using it for. Now, one thing I want to point out here is to pay attention to the units, because there is already a trick on all of your exams, because this table has a trick in it, right? If you look at the units for density, or excuse me, dynamic viscosity, we have built into those units 10 to the -3. So I'm not intending to trick you. That's why I'm telling you right now, don't let yourself be fooled by the problems in the exam. When you see these numbers, you have to appropriately write your units, right? So it might be 1.307 for a given value times 10 to the -3rd kilograms per meter per second, right? So include all of the unit here, and I guess they just did it that way in the table to make some sense. We're going to use these in the context where we're dealing with kilograms, meters, and seconds. and it would look pretty awkward and be difficult to see exactly how many decimal places if you wrote 0.0001307, right? It's just would be a lot, I guess. So don't be tricked. Check your units. Okay, a couple of units that I want you to commit to memory that you might not have in memory. 1,000 liters, so this is 1 liter bottle, constitutes 1 cubic meter. Okay, you'll need that conversion, and you're not always going to be able to, let's say, Google that on an exam. And that's not something I'm planning on giving you. So commit that to memory. The liter to cubic meters, 1,000 liters in a cubic meter. And if all else fails, you can estimate, right? You know what a 1 liter or a 2 liter bottle looks like, and you probably could imagine what 1 meter would look like. You know, it's about 3 feet, a little more than 3 feet, and that would be a cube. Well, how many of these could you fit in there? Not quite sure, but it's going to not be less than 100 and probably not more than, 10,000, right? So you're at least kind of close. So estimate as best you can, and that could even get you there if you remember that something about it, that it's a pretty direct or a pretty direct comparison. Okay, so in line with that, one thing to note here with the 1 milliliter in 1 centimeter, you might be thinking to yourself, what just happened? Because there's 1,000 liters in a cubic meter, but only 1 milliliter in 1 centimeter, 1 cubic centimeter. Well, if you're going to convert units, just a quick reminder, in a conversion like this, you have to cube the conversion, right? So if we were to say 1 meter should be 100 centimeters, and then we want to convert, we're doing that conversion, that's pretty obvious, that's no problem. But what about a cubic meter? Well, 1 cubic meter is going to be not 100 centimeters cubed, it's going to be 100 cubed centimeters cubed. So put the brackets outside the 100 there, and then you're good. Okay? So if you go back and check that, then this conversion will make sense. There's 1,000 milliliters in 1 liter, and there's 1 million cubic centimeters in 1 cubic meter. Okay, feels funny when you say it. That's the way it works. All right, so I'll give you a quick little thing to get your gears spinning. If the density of water, if we were to look it up, and we see the density of water at 5 Celsius is exactly 1,000 kilograms per cubic meter. Then find how many grams are in 1 milliliter of water at that temperature. Some of you probably already know. But do it. I suggest that you do this as just a little practice. Just take a moment to do the unit conversions. All right, so hopefully you had a chance to think about that a minute. And the answer should be 1. Right? It's 1 gram per milliliter. And in fact, if you've spent much time in a lab, you might have even calibrated an instrument or a pipetter or something based on how much mass there is in 1 milliliter of water. To do that explicitly, there's probably a few routes you could go there. If you first convert from the cubic meters to liters, those cancel pretty nicely. Even the 1,000 cancels, so you're left with 1 kilogram per liter, which is a pretty good thing to remember as well. That's actually part of how we define a kilogram, or that relationship. So then we could take this and say, well, from here, we're really dividing both of those by 1,000. So we could write all that out, 1,000 grams per kilogram, 1 liter with 1,000 milliliters, 1 gram per milliliter. Okay, make sense? Again, apologies that it's too obvious. I really want to guide your thinking here just to make sure that we're thinking about how to convert things, stuff like that. So next up would be number to mass conversions. Now, this is actually what chemistry is all about. But if I were to tell you that 1 egg weighs like, let's say 5 grams, or let's say maybe 20 grams or something, and then I ask you how much a dozen eggs weighs, you'd be able to tell me, based on how much each one weighs. Well, a dozen is the same thing as a mole in the sense that it's just a number. We say 1 dozen to mean 12. And we say 1 mole to mean just 6.02 times 10 to the 23rd. It's a number unit. It's that many of something. You could have a dozen molecules, you could have a baker's dozen of molecules, you could have a mole of molecules, right? That's what it's about. So if that's ever been your hang up, hopefully we can clear that up, and I've got another slide on that. Okay, so concentrations will be everywhere in this class, and the simple, stupid definition is some amount of stuff in some other stuff, right? This could be some heavy metals in soil, right? So it could be chlorine in water. It could be a variety of things. It could be particles in air. Typically, we'll have some denominator like liters, cubic meters, occasionally grams or kilograms. You could do how many kilograms of soil. So you might have X number of milligrams of this contaminant per kilogram of soil. And sometimes we'll do parts per X. So parts per thousand, parts per million, trillion, billion, whatever. And actually, that sounds kind of weird. Okay, parts per thousand, what does that mean? You've actually been doing it for a very long time. Parts per hundred is extraordinarily familiar to you. That's called percentage. Okay, so parts per hundred that's straight up what we mean when we say percentage. What percent? So if I tell you you have 1,000 parts per thousand, it might take you a moment for that to sink in, but that's exactly like I said, that's 100%. 100% you immediately know, right? Exactly what I'm talking about. That's everything. That's all of it. Whatever it is, that's all of it. But if I say you've got 1,000,000 parts per million, your brain's just like, wait, hang on, what just happened there? And then you come to it. That's fine. I just want you to know that's the relationship. So you could have 1 part per million, and that's if you put it as a proportion, that's 1 over 1,000,000. Just like you could have 1%, and as a proportion, that's 1 over 100. Okay? So that's the way to think about it. And you'll even notice that parts per thousand has the percentage symbol with an added 0. So I guess we could probably add a bunch of zeros for parts per million if we wanted to. Okay. Occasionally you'll see parts per million by volume or something like that, but more typically it would probably be like by mass, I guess. All right. So speaking of concentrations, when we deal with chemistry, it's really important that we're not mixing mass with number when we needed a proportional difference. Okay, so if we need to know molecule A reacts with molecule B, we cannot compare them on a mass basis because molecule A might be 100 times heavier than B, but it's a one-to-one relationship in terms of how much reaction happens. So when we talk about a mass concentration, like milligrams per liter of hypochlorite here, that's much different than talking about the molar units. So when we need to convert to molar units, we need to remember, like I said earlier, 1 mole of X is 6.02 times 10 to the 23rd of X, whereas 1 dozen of X is 1.2 times 10 to the 1 of X. And I said it that way just to get your mind, again, thinking about it. You know what a dozen is, but you've never ever thought of it as written out this way, right? 1.2 times 10 to the what? That's 12, right? A fancy way of writing 12. So you know this stuff even if you hate chemistry, and maybe you just didn't know you knew it, okay? So how many eggs would it take to properly egg a car, right? Let's not actually be vandals, but if we think about it for a moment, like what would be your guess? Okay, one would do it, okay? Anybody a little more creative or malevolent or here I'm thinking, okay, well, if I wanted to be really thorough about it, maybe 1 for each window, maybe 1 for each door handle, you know. Maybe I'm the... But you would not take a proportional mass. You would not compare, oh, this car weighs 2 tons. That car only weighs 1, so I'm going to do twice the amount of eggs, right? It would probably be just like a 1-to-1 ratio, or a, you know, if you're really, really mean, a dozen-to-1 ratio, right? It would be a numbers basis, right? So think about that anytime you're annoyed with converting between mass and moles. We're talking about the number, and the reason we can't compare is because it would make no sense at all to take 1 ton of eggs to egg a car, right? It might make sense to take 1 egg. If we're not encouraging vandalism or anything, but that should explain, hopefully, why we can't compare molecules on a mass basis when we're talking about chemical reactions. All right, that's the point I want to make there. Okay, so quick review then. The periodic table gives us some information on how much each egg weighs. So we can convert from the weight of eggs we need given some number of cars, right? Or however we need to solve a problem. That number here is the atomic mass, or if we have a molecule assembled of several atoms, then that will be the molecular, sorry, I said it. Yeah, atomic mass or atomic weight or molecular weight. So that number is how many grams that a mole of this substance weighs, right? So we've got this many moles. 1 mole of hydrogen is that many grams of hydrogen. And for most of the time, you know, we don't really need that level of specificity for the class, so 1.0 grams per mole would probably be fine. Okay, molar concentrations. Whenever we're talking about concentrations of a chemical and we have it in a number basis, that's molar units. We're always going to report in molar units. And again, just think of, we're talking in dozens. How many dozens of eggs, right? How many dozens of molecules? How many moles of molecules? And then we're adding it as a concentration, so it's how many dozen of molecules per liter, right? So this is a concentration unit that takes, in some volume, there's some number of our molecules. So that we can describe as capital M or moles per liter. These are both acceptable units. And anytime you see brackets and some chemical, we know that that is moles of X per liter. always, always, always brackets mean moles per liter of that thing. Okay, so when you have a formula, when we get to chemical equilibria, you'll have cases where the equation has brackets. You know you have to go from mass to moles, or to be in moles regardless, in order to solve that. To compare, so we're not taking a tonnage of eggs versus a tonnage of cars, right? Doesn't make sense. All right. Another type of units that we will use would be a kind of a proportion of numbers. So in number concentrations, we'll often say N for number of, let's say, germs, microbes, whatever, per liter. And when we compare what we start with to what we finish with, we often see this very common, kills 99% of germs. Now, if you didn't know what the Lysol or whoever they're advertising, what they're not saying is they tried every single germ that exists and 99% of those were susceptible. That's not how it works. Instead, they took one particular type of germ, exposed it to their conditions for some amount of time or whatever they were doing, and out of 100 of them, 99 of the germs died. So they killed 99%. So 1% remaining. So you might see these as 99.9% or 99.99% or whatever. So this way of talking about it is very common, especially for disinfection type of studies and similar stuff. And really what I want to point out here is if we compare our N, which would be some current number concentration, we'll say number per liter, to our initial, maybe we divide, this would be initial number per liter. This is giving us the proportion that's remaining, right? This is a fraction, and let's say if we're killing bacteria, then we have less than what we started with, assuming we killed anything, right? At most, we have exactly the same amount. So if nothing died, then we have 1 as a fraction remaining. But overall, this would be our fraction remaining. And we could do 1 minus that fraction remaining. And I think I have all this on the next slide, actually. Would be the fraction removed. Okay, so if we take a look at what that's going to look like, but one more comment before I go. Oftentimes when we're dealing with bacteria or viruses, we have particular units called colony-forming units or plaque-forming units, and this would typically be per milliliter, maybe per liter. So a way to count them by growing them on a petri dish and counting the colonies maybe, something like that. We've done a lot of that in my lab. So there are ways we can quantify them, especially living or infective microbes, and then we're going to count that number per volume and then report that. Okay, so if N over N naught is the fraction remaining, 1 minus that is the fraction removed. So in the example of if we have N equals 1 afterwards, our N over N naught is 1 over 100. That means that 0.01 is remaining as a proportion. We could say that's 1%. And by the way, since we were talking about it earlier, we could say that's 10 parts per 1,000 if we wanted to, right? Just to confuse ourselves a little bit. So we'll not leave that there. Okay, that means that the amount removed would be 1 minus 0.01 is 0.99 removed, or 99%, right? So this is how we, again, another one of these cases where this is intuitive, you know this is nothing new. But I'm just pointing it out here because we're going to be using a lot of this, and I want to make sure you're clear on how we translate so it's not, you know, you don't get to this point on an exam and you're like, what the heck am I doing? You know, have a brain fart and not be thinking about how to convert from remaining to removed or dealing with all of this. So familiarize yourself with this. Another concept here is what we would call a log reduction. This is basically shorthand, but it's very commonly used in especially disinfection, also sometimes membrane sciences and some other areas. What we're referring to is if we have a 3 log reduction, we've moved the decimal places 3 logs as a log base 10. So log base 10, we know that every single one of these, that's 10 to the minus 3, right? So a 3 log reduction is 10 to the minus 3. That's, if we were to write that out as a decimal, 0.001. We moved the decimal 3 times, and that corresponds, as we see just up here, to a 99.9% removal, whereas a 4 log reduction would be 10 to the minus 4. You could also do a 4 log growth and have it as a positive 4 and go the other way, right? That would be a multiplier of 10,000. So in this case, a 4 log reduction would be 0.0001 or 99.99%. So as you might see, saying 4 log is a lot easier than saying 99.99%, right? So it's shorthand, it's used really often. It's just a matter of log base 10 and understanding that, okay? And it relates exactly with this, the fraction remaining, fraction removed kind of stuff. We will have problems in part of our sedimentation and coagulation kind of stuff where we cause particles to stick together, make larger particles. We're going to be counting the number of particles, and maybe we'll be solving for n over n naught given some other conditions, okay? So sometimes we'll have cases where it's not exactly a clean 4 log or whatever. All right. Okay, so mass balances. We mentioned it earlier, and we're going to start on this. We have one little problem I'll have you do, and we'll pick up there next time. But a mass balance, really we're defining an accumulation of something in a system, right? So we have, typically in the case for what we're going to look at is some sort of flow rate. I said earlier, typically we're not going to mess with that changing. So the flow rate, we're going to have the same flow rate on both sides. And then maybe we'll have some concentration of a contaminant coming in, and I'll call that C naught, or C initial. And then some contaminant leaving. Now, what we're defining is some sort of a control volume here, where we're looking at what happens inside that. So what's coming into, what's going out of, what's crossing the boundaries here, and also what might be happening inside of it. So we have some volume, we might have some reaction, and perhaps in this case, we'll say that it's well mixed. We will have cases, we'll look at this next time, where we might have a reactor that's not well mixed and it's kind of flowing more like a plug of water through a hose or something, okay? So we'll explore that later, but the same principles can ultimately apply. So the accumulation rate, again, all of these will be rates, right? This is going to be a mass per time equation. So the accumulation rate is at what rate is our concentration C accumulating inside this vessel, okay? Or the pond or whatever it is. So we can define the accumulation rate as let's just say for the moment, some accumulation, and what that's going to be equal to is whatever we have coming in. So the input rates, it could be multiple, right? We could have multiple streams coming into one pond or lake. We then have some number of outputs yielding an entire output rate. And then perhaps we have some reaction. And this could be a positive or a negative. So it could be a growth or a decay reaction, or maybe both. Maybe we have two different growth reactions and one decay reaction. Whatever the case, we can capture that in this reaction term. It's basically what I wrote out here. You could write this reaction term as growth rate minus decay rate. And if we have a condition where we reach a steady state, meaning there's a constant amount of C in the system, even if we're decreasing it from start to finish, but if there's a constant amount per, like in that volume, then we would say that's a steady state. The accumulation has reached zero. That's like the case where we had a dam for a pond, it filled up, and then now you have a constant amount of water entering and leaving. Right? That's has reached steady state with respect to the amount of water. Okay? So we'll do the same thing with a lot of our problems. If we suddenly remove something, cut off the reaction, remove the dam, things start changing inside the system, that's going to be a non-steady state. We're not going to do too many of those. But mathematically, we will be able to do them, and you'll see how. We're going to get into the actual math of it next time, but based on this principle alone, we have a simple problem that you can go ahead and solve. Okay, so take a couple minutes and look at this problem. I'll read it to you and make a note and then give you a couple minutes. So we have a stream flowing at 10 cubic meters per second, has a tributary feeding into it with a flow of 5 cubic meters per second. That's this tributary here. The stream's concentration of chloride upstream, that's Cl minus if you care, is 20 milligrams per liter, and the tributary chloride concentration is 40 milligrams per liter. So we have some stream that has a little bit higher salt concentration, essentially, coming in. And it says treating the chloride as a conservative substance. That's telling us, that's a key word for us, to say that there's no reaction. So there's no reaction term. And we assume that in this little dotted thing here, they're completely mixed. So now the chloride concentrations have been fully averaged across. Find the downstream chloride concentration. So you could do this with no environmental engineering or whatever thought, no thought to a mass balance. You're quite possible of intuiting this problem and approaching it. But what I want you to do is take a thought here to look at it in terms of accumulation, which in this case, we can imagine there shouldn't be any way we're gaining more and more chloride in this little bubble or pocket here, or any less if the two streams are constant. It's just going to be steady state. So the accumulation should be zero, and we can put that in terms of inputs minus outputs plus some sort of reactions, which are zero. So from that perspective, go ahead and solve the problem. So just a quick note here. We'll pick up here next time, but as you approach this from this formal mass balance of thinking, what you would do is notice that you can solve this mass balance equation to become inputs equals outputs, and then you know your inputs, so that would be the Q times the C plus Q times the C for the waste equals the Q times the C for the mix. So we can resume there next time, and have a good weekend.